So CPU, a central processing unit, is a complicated piece of silicon with several different subcomponents. We're going to call something the arithmetic logic unit. That's really enough. We're going to say that it has registers, which are places to store numbers. Maybe this isn't just got 3 registers. 3 places to store numbers. And it's got a place to hold an instruction or a sequence of instructions, otherwise known as an opcode. What am I going to do with these numbers that are in memory? And then it's got outside of that a timer that is driving it. So as the CPU is getting ready to do something, I had planned on writing. That's why I raised that, isn't it? So every click of the clock, it can do one thing, ignoring the fact that now there are chips that can do more than one thing at the same time. It can load information into one place, or it can add 2 numbers, every click of the clock. So what will happen is we're going to just invent a dummy little language. The central processing unit and the timer, and then somewhere else there will be memory, RAM. Think of that as paper tape that has 1,000,000 different places on it, or 1,000,000,000 different places for numbers to be written on it. And 1,000,000,000, a gigabyte, or 1,000,000, a megabyte, or whatever. A kilobyte is 1,000 bytes. So anyways, we have some memory. We're going to invent our little language. Our language, we're going to say that we have some opcodes. We have the opcode 1, which means store a number into register 1. And then we have an opcode 2, which means store a number into register 2. Then we have one that says read from the address in memory 1. And then we have one that says read from the address in memory 2. And we have another opcode that says add register 1 to register 2 and store in 3. And then lastly, we have one more opcode which says write register 3 to the address stored in register 1. Okay, I'm not going to spend a lot of time actually getting this to work, but we're going to pretend that this is our little language. So our program, the computer, will be feeding the CPU a series of numbers. Let's say that we're sending the number 1 and 10 to it. And so we have 3 registers, 1, 2, and 3. What is opcode 1? Store a number into register 1. It's going to write a 10 there. And then our program has opcode 2. The fact that these are all sequential is just because I was making it up. Store a 20 into register 2. Opcode 3, read from the address in memory 1. Now, it would really need to specify where it's going to read it to. So we have some RAM out here. Each byte in RAM contains a different digit, or different number. We're going to say that we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10's got an 8 in it, let's say. So read from the address in memory 1. And so it loads up here. 10 has a value of 8, and so we're going to put an 8 there. And then it finds the next command. Read from the address in memory 2. Well, address 2, I'm going to change that to a 2 rather than a 20, so I don't have to write a whole bunch. Let's say that number 2 has the number 100 in it. So we replace that with a 100. The clock ticks again. We go to the next instruction. Add registers 1 and 2. So then it adds 8 and 100, and in register 3 we have 108. And then our last one down here, which I kind of let scroll off, was 6. And so the last command in our program was 6 and then some memory address to write to. We're going to write this back out to address number 10. So write what's in register 3 back to the address stored in register 1. So it would, well, register 1 still has a value of 8. It would go and store whatever is there into that position, whatever is stored there. So it would go out to 8, and it would write 108 there. So you can see what's happening. Step by step, a series of numbers are being sent to this chip, and it's executing them one at a time based on the values stored in the registers, and it's manipulating the numbers in RAM. Now, obviously, it's far more complicated, far more powerful than that. But that's what, a computer written in the 40s, made in the 40s, would have been capable of doing. Something like that. Nowadays, CPUs have, billions of transistors on them. And so they're extraordinarily powerful. And nowadays, they don't just do one thing at a time. You have multi-core processors, which are actually multiple CPUs on the same chip. So they can be doing 2 things at the same time, or 4 things at the same time, or 8 things at the same time. And this is ignoring the fact that there's got to be some communication between the chip and the hard drive. So that there's actually another processor controlling moving data from the hard drive into RAM so that you can read a file, read these numbers in, or you can send these numbers back out to RAM. And then there's another processor that's capable, that controls the interface between this and displaying things on screen. But anyways, so we have our central processing unit. It can do arithmetic and logic. What do I mean by arithmetic and logic? This is integer math. What are integers? Integers are whole numbers. 1s, 2s, 1,000. 3.14159 is not an integer because it's got that fractional thing. It's got 14159 on it. And logic. Logic is an evaluation that produces either a true or a false. And inside the computer, that boils down to being a 0 or a 1. 0 meaning false and 1 being true. So, compare the numbers stored in these 2 things. And if they are the same, put a 1 there. Else, put a 0 there. Are these 2 numbers the same? Yes, they are. That's true. Is this number greater than that number? That might not be true. That's a false. So you have your integer arithmetic and then your logic. So that's one part of the chip. Then there's another part that does floating point math. Floating point is when you have 3.14159 non-integer numbers. And so that's a different part, different arrangement of the transistors optimized to handle large numbers, that with a decimal point. So we're going to hit these terms again, but we're just going to write them down here. An integer is a whole number. 1, 3, 1,000, whatever. Floating point is a number with a fractional component. Even if that fractional component is 0. So 3.14 is a floating point. So is 1.0. If I ask you if the number 1, is it an integer or a float? That's an int. If I ask you if the number 1.0 is an integer or a float, the mere fact that it's got a point in it makes it a floating point. Even though these, to our eyes, look the same. 1 is equal to 1, right? Yeah. Inside the computer, they're stored completely differently. Integers are very easy to store in a computer. Floating point, you have to decide, okay, you're going to have a mantissa, which is the part that's at the beginning of it, and then it's times 10 to the power of whatever, and so you have an exponent component. Every floating point number consists of 2 chunks of information. Because if you express 1.0, well, let's do a different number, 301, you would, or 3.01, there we go. You would say that that is 301 times 10 to the power, I'm going to mess this up, whatever, but you get the idea. 301 times 10 to the power of negative 2, I believe, is 3.01. This is the mantissa, and you don't have to memorize these terms. I just want you to get the idea that these are very different things in RAM, in your memory. Let's just even make that 3.0. There we go. So 3 is 3 to the power of 0. So the mantissa is 3 and the exponent is 0. So it has to have 2 places in it. In order to express that, you have to have a 3 stored and you have to have a 0 stored. 30 is 3 times 10 to the power of 1. So inside it, it's going to have another 3. And then it's going to have a 1 as the exponent, the 2 places that are stored. Whereas the integer 30 is held completely differently. It's just written out in memory as a 3. It's written out in binary. It's written out in zeros and ones. So that you can see that the structure is just completely different. So if you asked the chip to compare those 2 things, it really can't, because they're in different formats. One would have to be converted to the other. Okay, enough babbling about that. Let's go back to this. So we have the CPU, and then we have memory. RAM, random access memory, so that it can pull numbers anywhere out of that memory and put them in the chip to do something. So like if you have a graphic loaded in memory, this is just a series of numbers that make a picture. You know, each pixel has a different color in it. That is loaded in RAM so that it can be then sent to the video card to be displayed as a picture. All, you know, if you're typing a resume, you know, your name, Bob, B-O-B is stored in RAM. Everything that you're typing is stored in the RAM. And then when you want to save that document, it's saved somewhere else so that you can turn the computer off and then come back. So along with your RAM, you have to have some kind of storage. If you didn't have storage, it wouldn't be very useful. If I typed in a resume and I printed it out, and then I realized 2 days later I needed to make a correction, it'd be a real drag if I had to type it all in again. That's the way typewriters work, right? You have to, you know, type your whole resume in again because you misspelled your last name. Computers are nice because you load up your resume, you make that change, and then you print it. So you need to be able to store data somewhere and then be able to read back. And nowadays people talk about the cloud. My data is on the cloud. You know, that just means that it's stored on a server on the internet somewhere rather than on the device itself. So storage media is the material on which the instructions are stored. Nowadays there's different kinds of storage media, but traditionally it was some kind of magnetic film. If you think about it, your disk drive is just platters of magnetic media. A floppy disk is just a very thin platter of magnetic film. A tape drive is, you know, a strip of magnetic tape. But then there's other kinds. You know, there's CD-ROMs. And instead of being magnetic, a CD is not magnetic, it's optical. So the CD-ROM the writer goes and it burns holes, you know, in a specific pattern, pits in the surface with a laser, and then later on when it wants to read them, it understands, you know, what those different shaped pits mean. So you have your media and you have your storage device. Your device is the thing that uses that media. It writes to that media or it reads from it. So the disk, the floppy disk is the media. The floppy drive is the device. The CD-ROM is the media. The CD-ROM drive is the device. And nowadays it all seems kind of nebulous. I pull out my phone, I don't see a disk drive on it. You know, the media is electronic. It's flash RAM. And then the device is also the flash RAM. So, you know, these terms don't really make as much sense anymore, but conceptually we can still think of them as that. Here we go. There's our medium, and then there's our device. Or a hard drive. It's got several different platters of very high density. And then you have these heads that move over the platter reading it. So that's the device, and then whatever's on the hard drive itself is the media. Then miniature storage media. Miniature storage media is where the media and the storage device are all contained on the same unit. You have an SDD card. It's got all these transistors on it, which can either be set to zeros or ones, and it's also got the ability to change that. So it's a device unto itself for your digital cameras or whatever. Why are computers so powerful? They operate quickly. I'm going to look up a picture here. ENIAC is considered to generally be the first electronic general purpose computer. There were other people working on making electronic general purpose computers at the same time, but in America during the World War II, this was kind of the pinnacle. It was the first one that was electronically programmed, that had memory that could be read from, memory that could be written to, and storage. So this was one computer, all of this junk. And you programmed it by hooking up patch cables to different places, just like a telephone operator. Please correct me to room 3. And she had to put up two cables hooking up 2 different slots. Same thing. You had to program it by wiring it like that. And it didn't have transistorized RAM. Memory on an old computer of that era would have been stored probably on vacuum tubes. How would you store? A vacuum tube is just a fancy word for light bulb, really. Or you could say that a light bulb is a vacuum tube. But they were a little more sophisticated than that, obviously. But if a vacuum tube was dark, it was off. That's a 0. If it was lit, that's a 1. That'd be the most primitive one. Now, other kinds of vacuum tubes might be able to store, like, it might have 10 different levels of brightness to represent a number between 0 and 9 or something like that, so it could hold different states. But that was the memory of a computer. It had all these tubes. And you can bet that those tubes burnt out. And so, there were people whose full-time job was going and trying to debug the computer and figuring out which devices, had burned out so that they could then replace those tubes and keep it running. That computer, the ENIAC, ran at a rate of about 300 instructions per second. It could do 300 different pieces of math per second, which was amazingly fast at the time. Imagine if you gave somebody a book of figures and you said, I want you to add up these 300 numbers, or I want you to do 300, I want you to fill out this multiplication table, so I want you to multiply something 300 times. If that guy was amazingly fast, he might be able to do 1 a second. Probably a lot slower, unless the numbers were really small. This could do 300 of them per second. Nowadays, you buy a computer and, at a minimum, it's probably a 2 gigahertz computer. 2 giga means billion, and hertz means per second. And the phones and your tablets and stuff like that operate at least at a speed of 1 gigahertz, 1 billion operations per second. So if this thing's operating at 300 per second, and nowadays, something operates at 3 billion per second. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then, how many times faster is that? That's 10 million times faster. So a modern chip could do math 10 million times faster than, that thing with the mechanical relays and the vacuum tubes. You could add 10 million numbers up, in the time that it took this one to add up one number. There was something called Moore's Law invented by, named by one of the founders of Intel. And the idea was that every 1.5 years, the speed and the storage of an electronic device would double. And so if we were going to count from let's just say from We're going to pretend that that's 1950, and we're going to go up to, I don't know, yeah, 2016. Let's see if we can get that going. So every year and a half, let's simplify that. Let's say every 2 years the processing speed doubles. So maybe by 52 the processing speed went up to 600 instructions per second. 54, it went to 1200 instructions a second. 56, it was double that. 58, it was double that again. So by 58, we're at 4800 per second. I'm going to round that to 500 to 5,000. So by 1960, it's doubled again. We're at 10,000. At 62, we're at 20,000. 64, we're at 40,000 instructions per second. 68, you can kind of see that this is getting really big, really fast. By 1970, we're doing 100,000 instructions per second. By 72, we're doing 200,000 instructions per second. I'm using K because K stands for kilo, which is a Greek prefix for 1,000. And then 74 would be 4,000, 400, 76 would be 800, 78 would be 1,000,000. So that's 100K, 1,000K, which we can then replace with 1,000,000. We're at 1 megahertz by 1978. M stands for mega, which stands for million. So we keep going. 1980, 2 megahertz. 82, 4 megahertz. 84, 8 megahertz. 86, 16 megahertz. 88, 32 megahertz. 1990, 64 megahertz. You know, there's obviously a better way of doing this. We're going to write a program to show this. Doing this is just really annoying. This is the kind of thing that computers are good for. So let's all crank open idle. Either search for it in the search bar, or if you anchored it, you know, docked it in the taskbar, just go to the start box, type in IDLE, click that. Once it comes up, it'll say Python shell. A shell is something which you can execute programming commands in directly. Like you could say A is equal to 2, and then you could say B is equal to A times 2, and then you could say print B. And it fails. That's because I typed a lowercase here, and this one was uppercase. They have to be exactly the same. So, okay, print B. Well, if A was 2 and B is equal to 2 times that, then B would be 4. Okay, so that's the shell. We're not writing a program here. We're giving it individual commands, almost like you had a really incredibly powerful calculator. You're just telling it to do one thing at a time. Instead, we want to give a sequence of instructions. So we're going to write a program to do this. So I click New File, or File, New File. And I'm going to save this. I'm going to do a Save As. I'm going to save it to my programming subdirectory off the desktop, which I called CIT1113-7078. Actually, I'm just going to leave it on the desktop. And I'm going to call it more, or more.py. Py stands for a Python program. Why am I calling it more? Because we're talking about Moore's Law, and Gordon Moore, one of the founders of Intel. Okay, so what are the pieces of information I want to track? I'm just going to add some comments to my program to help me think. A comment is something that is ignored by the program, but the human can read it to try to make sense of things. All of the comments in Python start with a pound sign. In other languages, they start with other things. Like if you've seen Java or C programming or something, you may have seen double slashes. That means a comment in that language. In this case, okay, so I want to keep track of the year, and I want to keep track of the speed, the number that kept increasing, and then that number that it was increasing by. you know, when I said it was doubling each time. So what am I going to call that number? Yeah, the multiplier. And how often that increases. So we're going to call that per year. So when I was demoing it and typing everything in, I said that the multiplier was 2 every 2 years. But instead we're going to be fancy, and we're going to make it multiplies by 2 every 1.5 years. Now this isn't programming, this is just commenting. I'm just thinking these things out. Okay, so my starting year, I'm going to start in the year 1950. And I'm going to say that in 1950 the speed of a computer was 300 instructions per second. Now we're going to be doing some stuff here that you just have to kind of take on faith, since we haven't really talked about any of this yet. I'm going to write a loop. While the year is less than or equal to 2016, colon. Print the year and the speed. Now I've only defined 2 of these variables that I mentioned. We also need that multiplier and that per year. So I'm going to go back up here and add 2 more things. I'm going to add a line for mult and one for per year. So our multiplier is going to equal 2. Our per year, why don't I just say per, is equal to 1.5.
Does it, in Python, does it matter if there's a space between?
No, spacing is not, spacing is critically important in one place, but it's not important there. I could have typed that one like that while I type this one like that. Totally cool either way. That's called white space, and you'll hear that term. Where spaces are important are when you're tabbing. You have to match your tabs up completely. You can't use 3 spaces for a tab here, and then later on use 4 spaces, and then later on use 2 spaces. It has to be exact. And that's in a contrast to other languages where the tabs don't have to be exact. Okay, so we're going to print out the year and the speed, and then we're going to increase the year by this amount, by the per year amount. So year is equal to year plus per. And the speed is equal to speed times the multiplier. And that's about enough. So I'm going to stop indenting and print a done message. So this is what's known as a while loop. A while loop will repeat all the code that's indented over and over and over until this condition is not true. So as long as our year counter is less than this value, it's going to keep doing this. It's going to print the year, it's going to add something to the year, it's going to change the speed, and then it's going to come back up here and check it again. Is the year still less than that? If so, it's going to repeat over and over and over. And finally, since we keep adding stuff to the year will no longer be less than or equal to 216. It will finally exit the while loop. So indentation is very important in a Python program because it indicates what pieces of code are attached to what loops. In other languages, you do other things. Don't type this, but I'm going to demonstrate. Other languages might use curly braces to indicate that this code was blocked together. And that's kind of nice because in that case you don't have to use, indentation, although you still do to make your code look readable. Python, nope. It has to be indented, and the indentions have to be exactly the same for everything that's under it. But then when you stop indenting, it means that code block is done, and so this is outside of the while loop. Now I'm going to run it. So the first thing I'm going to do is save it. Not that I have to do that because when I run it, it will save it. If I have not made any syntax errors, it will actually run. But of course it says invalid syntax, and that's because every change in indentation has to have a colon in front of it. And so I forgot the colon on my while statement. Okay, if Moore's law was accurate and we started off with 300 instructions per second, then by today our computers are this fast. Now that's probably actually not true. That would be, my brain can't process that, so I'm going to come back over here and add commas to it to make it legible. Okay, so that's thousands, that's millions, that's billions, that's trillions. Obviously, that's not a real good estimate. Let's lower the per to once every 2 years rather than 1.5 years. So I'm going to make a change. I'm going to change the value of that variable. Why is it called variable? Because it varies. It can contain different values while it's running. And then I'm going to run it again. Yep. Maybe more like it. Again, I can't read that without the commas, so I'm going to come back in and manually add the commas. Thousands, millions, billions, trillions. That's a little bit better. Okay, so the difference is probably, well, there's a couple of things that are going on. Moore's law plateaued at a certain point. The speeds, the increases in processing speeds, one of the things that helped was making the smaller and smaller chips. Because the less distance a signal has to go from one part to another part, the faster it is. You know, those electrons are moving around nearly at the speed of light. But if that electron had to go, you know, for a nanosecond in the speed of light is about this far. So we would not be able to do as much as if we were able to shorten the distance between these two components to an inch. Then it would be able to work, 10 times faster. And then if you were able to shorten the distance of that, to 1/10 of an inch, it'd still work 10 times faster still, and so on. But there's a limit to how much you can miniaturize the processes of the chips. They're down in nanometer sizes. Each trace on the chip is, like they talk about a 30 nanometer process or whatever. You kind of hit a limit on a couple of things. One is how small the traces can be, and two is how much heat is generated by the processing. Because it is a device, and each time those states are changing, some work is being done, and it's generating some heat. And, y'all who are power gamers or whatever, you may have built your own systems, and you put a massive fan in there to keep your system cool. And it's because the chips in there are generating heat as they work. So there was a plateau where it could not match Moore's law anymore. The way around that was then to start bundling multiple processors, multiple cores into the same chips, so that it could do two things at once rather than just one in a 2-core chip, or so it could do 4 things at once rather than just 2. And so they're trying to work around those absolute limits. The smaller in size, you hit a limit in the size, but you can get around that by trying to get a chip that'll do more than 2 things, more than one thing at a time. I wish that had worked out a little better. I wish that it actually kind of pegged out at 3 billion, I'll have to research and come up with a better example. I probably should have started it at a different year with a different number. It might have modeled reality a little bit more. If we were going to make this program more flexible, we could have it ask the user, what's the starting year? What's the ending year? What's the starting speed? What's the multiplier? And increment that multiplier how many times, once every 2 years or whatever. We could ask for all that stuff, and then it would look like the processing cycle that we saw in that slide. Gather your input, do your processing, display the results. This idea of a while loop is pretty powerful. We could write a program that would calculate interest for, say, 10 years. Let's do that. Let's just tack that on to the bottom of our program. We're going to have a variable P that stands for principal. It's the starting balance. And we're going to start with $1,000 in the bank. And we're going to say that our interest rate, R, is equal to 5%, 0.05 per year. And we need a counter to determine what year we're currently on, and we need another. So let's just have a C, well, let's call it year. Years 1. Now this loop is going to look a lot like this loop. While the year is less than or equal to 10, because we're going to run for 10 years. While year less than or equal to 10, colon. I'm going to scroll this stuff up so that it's not hard to see, so nobody in the back has to stand down there. Stand up. Read. While the year is less than 10, print the year and the principal. Now we have to calculate a new principal. Your interest is equal to the principal times the rate, and then your principal is equal to the principal plus the interest earned. Now that could be simplified or shortened into one statement rather than two. And then we have to add 1 to the year. Now here I called it Y and here I called it year. That's a syntax error. The program would not run. I need to call them the same thing. I'm going to change this one up here to year since I'd already used it. So where it said Y is equal to 1, fix that. This was Y is equal to 1. Change it to year is equal to 1. Now we're going to print done again. No, I'm not going to make that a comment. I'm actually going to print the word done. Done with interest. Now if I have not made any other syntax errors, then it should run. I've got a problem. The problem is that I have a while loop that's dependent upon a year, but I never increase the year. So year is equal to year plus 1. Okay. So after 10 years, at a 5% interest rate, compounded annually, I start off with $1,000 and I ended up with $1,500. Now, if you can find me a bank account that gives me 5% interest, I'll be really interested. Interest rates are pretty low, and they have been for the last couple of decades. But, you know, that is the power of compounded annual interest, is that it increases pretty nicely if you have, you know, a good interest rate on it. We could monkey with this. Let's say instead of 5%, it was 10%. I'm going to come up here and change the interest rate to 10%, 0.10. Then when I run it, it's a lot more money. Instead of being $1,500, $1,500, after 10 years, it's $2,300.
I think the reason mine is like it's continuous is because I didn't put the print on the same tab as like where while year.
Yeah, let me wander around and make sure that everybody has got this going.
Yeah, mine was just.
Okay.
And it's because
What's going on here is I did a change, which you don't have. This, we have to tack this on. The while loop is dependent upon the year variable, but if the year never changes, it never exits the loop. So tack this line on.
So it has to be inside of the.
Inside of the loop, add year is equal to year plus 1, and then outside of the loop, add the print statement. next thing we'll do, just for fun, is we'll make it ask for this information. What is the principal, what is the rate, and how many years? So we're going to add some statements to do that. And then we'll probably call it done. It's working for y'all? Good deal. Yes, sir. Need a colon there. Every time you start indenting, there has to be a colon before it. Now that we've stopped indenting, it has to be right against the edge, so take that space out. Take the spaces out of all these two. I know that for a while. But this is okay, because they're all indented. Okay. Good deal. Python is the only language, modern language, that is so dependent upon the way things are indented. All good? Good to go? Yours? So we have I is equal to P times R. Sorry, that's shift A asterisk. Okay. That's cool. Maybe we'll make that a shot. I mean, it is increasing. That's cool, but something that we off. Oh, it's not P is equal to P plus 1. It's P is equal to P plus I. It's just hard to do. That's the problem. Okay. There we go. Good back here? Any help? Cool deal. Oh. When you start using and outside of the tab, in spaces. There we go. It's a same thing. Close that, so what you're gonna have to do is take these tabs instead of spaces. Now the print state there is outside of the while, so untab it immediately, remove that space. Same with those two comments. Same with those three. And same with that. There you go. Okay. So some of the things that I noticed when I was walking around is that by choosing I, that looks like a 1. So some people were typing P is equal to P plus 1. Single letter variable names are not the best thing in the world. I was going with single letter variable names to try to make it the fastest possible to type. But really, I should have done this. Don't make this change necessarily. But I should have called that principal. And everywhere that I have a P here should actually have the word principal. And I should have called this rate. So everywhere I have an R, I should have the word rate. And then instead of I should call that interest. That makes a lot more sense to read, right? It's much more comprehensible to understand what it's doing like that. So single letter variable names are kind of, for the birds. I shouldn't have been using them. But that being said, since we did, I'm going to undo all those changes. Let's make the program ask the user for the principal and for the rate. So above our while statement, we're going to add some code. This will probably be the last thing we do for today. We're going to print what is the initial deposit. That displays a message, and now we want to get some input. So P is equal to input. But unfortunately, that input comes in the form of text. It's not a floating point or an integer, so we have to convert it. Now, you're not supposed to all know all this yet, but it's just to get a feel for it. What I'm doing is I'm demonstrating how it looks now, and then we're going to talk about what all this means later. Right now, I just kind of want you to accept it on faith. Now I'm going to do the same thing to get the rate, the interest rate. Print, what is the interest rate? And I'm going to even give the user an example. Example, 0.05 is 5%. Now that's a lot of typing, but I figured that might save the user. Because if they just type in 5 for 5% and then it shows them earning $1 million because we were really increasing it at 500%, then they'd be disappointed to find out that that's not the truth. The color coding kind of helps. Like if I forgot the last double quote, then it wouldn't look right because that last parentheses needs to be black to match that one. So R is equal to input. We're gathering that input. And then we have to convert that to a number 2. So I'm going to add some comments to this. This is what's known as a prompt. Tell the user what they need to type. Input is get input from the keyboard. And then the last statement is convert the input to a floating point number. Those are the 3 things. And of course, these 3 lines do the same thing as well. I'm just not going to put comments on every single one of them. But to make this a good program, I'm actually going to describe what P and R and year mean. So I'm going to add some more comments. I'm going to come up here and say P stands for principal, starting amount, money. And R is the interest rate per year, annual interest rate. And the year is just a counter. Now, it's quite possible I made syntax errors, so I'm going to run this and see. I'm kind of tired of this Moore's Law calculator eating up all my space, but I'm going to leave it. My initial deposit is $1. What is my interest rate? It's 500%. So at 500%, I have $10 million. I don't know if that's true, but whatever. I should have used more valid numbers. I should have actually used the numbers that we were originally using. So I'm going to have to run it again. Unfortunately, I have to rerun this program every time I want to change the data. We could make it loop, and ask the user over and over and over. Do you wish to continue? That kind of thing. But this is whatnot. Okay. The initial deposit is $1,000. The initial interest rate is 10% interest, 0.10. And when we're done, we have $2,300. Alrighty, I don't want to scroll this off while some of y'all are still working on it. So I'm not going to put these comments up at the top of the program, but that's where these comments should go. Put your name and a description of the program and the date. So My name is Jeff Thompson. This is an interest calculator, and the date is August 24, 2016. I would like for y'all to do that for every program you turn in. Put your name, put the date, and what the program is. Now really it ought to have a better description than that, but that's enough for now. This is what's known as a comment block, and you should put it up at the top of the program, but like I said, I didn't want to have to scroll up. Alrighty. How are we doing? You're stuck. Here's the thought exercise. If you're already done with it, make it ask for how many years. No, I would have to make that change for you. Let me let me show you this one change, and then I'll ask you to do the next part. You see where it says 10 down here? That's what's known as a hard-coded number. We're not asking the user how many years to go. We're just assuming they want to go 10. I'm going to replace that 10 with the word max, and then I'm going to, no, that's a bad number. That's a bad word. Too bad. I'm going to stick with it. Not a good word. And so up here I have to define what max is. Max is equal to 10. But if I changed it to 20, it would run for 20 years rather than 10. For those of y'all who have it working, make it ask for the number of years and store that result in max so that it could run for 20 years or 100 years or 2 years. So that is your little thought problem. Change this program to ask for max, which is a number of years. So the changes I've just made is I added this line right here, and I just changed this line in the while statement right here. You don't have to add those. That's just to let you know. Chose a bad variable name.
But you just to ask them, you just do the same thing.
Exactly right. Max is actually the name of the function, and we are erasing that function and replacing it with a numeric value. But I couldn't come up with a variable name off the top of my head, so I left it that. That's why it showed up as a different color. Yeah, now you're gonna have to say how many years. Yeah, you can do that, Max. That's cool. Excellent. Let me make a Dropbox for this. So for those of y'all who haven't done, you can upload it, and then I'll keep wandering around. Okay, there's a Dropbox now called In Class 1. So when you're happy with your program, go ahead and upload your PY file to it. Now we're also going to make some homework, but it's pretty easy homework. All you either need to do is to install Python on your home machine, or just create a note that says, I'm going to do my homework at school. I just want you to make that decision. So homework 0, install Python. And like I said, you don't have to install Python. I just think it's nice to be able to do your homework at home. So let's make an note.
If we want to make it ask for the amount of years, do we need to keep the max syntax in there? Or?
Yeah, because you're going to ask the user, you're going to say print number of years, and then you're going to say max is equal to input, and the max is equal to float max, just like you did the other ones. Okay, so homework. Go to python.org and download and install Python for your computer. You have different choices, whether it's a Mac or a Windows. Then find and run idle. Then write me a note saying either A, I installed Python and launched idle. It's actually called idle.bad if you have to do a search for it or whatever. Or B, no way, I'm going to do my homework at school. I'll expand these instructions a little bit, but that's the basic idea, right?
And you want us to send you this note in Word, in Python, or?
Yeah, either create a Word document or a text document and just upload that into the Dropbox. So write me a note in Word or Notepad or anything saying this. Save that as homework 0.doc or whatever. Upload that into the Dropbox. Alright, let me upload those instructions. I'll tack on a little bit more information later. Alrighty, if you don't have the in-class assignment done and you need to bail because class time is over, that's okay. If you do have the in-class assignment done, upload it to the Dropbox, bail, that's okay. Either way, just go ahead and upload something to the Dropbox so you get credit for being here and for working on it today. So go to the Dropbox, refresh it, go to in-class 1 and upload your PY file. And I'm going to wander around for those who still need help. Alright, I'll see y'all on Tuesday. Oh, hi there. Okay, it's not a problem that you missed class. I just wanted to warn you.
I was gonna email it, just slip of
No problem.
my mind.
No problem. Yeah, no problem.
Hey, Professor.
Yeah.
Just a quick question.
That's a different program, actually. That's the Moore's Law calculator. We could even delete that just to clean up our program. Let's scroll up. Okay, now, let's read everything from that line all the way down to this done message.
I'm gonna grab my hardware.
We don't need that anymore. Yeah. Now this is just our program. Now we're good to go.
Are you carrying it all with you right now?
Yeah, mistakes.
Okay, it's back at 1,000.
Bag. It's bag.
Yeah, I went 1,000, that's our deposit. Okay, then what is our interest rate? Let's make it 10%, so 0.10. Close this. I added something that not everybody caught. Tack this line on to where it says years equal to 1. Add that. Max is equal to 10 underneath it. Sorry about that.
No, it's okay.
And that word appears in a different color. That's just because it's a
Oh.
really bad variable name. It's the name of a function. I should have chosen it. I wasn't creative enough to get it.
Oh, okay.
Yeah, you got Python going.
Yeah, okay. I
That's
just
cool.
wanted to make sure it's the right version. Because there was two different versions I could do.
So can we find idle as well? Oh, where's that idle? Okay, there we go. Now we're in idle, so you can do file new and you can get this program running.
Yeah, no, I just like.
Yeah, good job. All right, well done.
Yeah.
Yes, sir.
I just wanted to figure out not to look up here, but figure out
Okay, I apologize. I'm gonna need you to tell me the question.
So, like you said, I think it's add max.
Oh, yeah, yeah. How? It'll look almost exactly like this. You're gonna print how many years to run, and then you're gonna say something like max is equal to input, then max is equal to load max. Now, usually I'll go out there for everybody to see, but that's how you would do it. You just copy these lines and paste them and then change them.
Okay. So I just, if I turn it like this, it's still okay.
Yeah, turn it in. You're still gonna get full credit. But it's a cool little exercise. So, you know, if you wanna do it at home or whatever. Does it run? Oops. R is equal to full, okay. You're gonna need the parentheses after the word input. And you're gonna need the parentheses R after the word, yeah, like that, yeah. Alrighty, no problem. At the end of a print statement, you have to add another quote and then a parentheses. There. Cool deal. Let's actually test it though. Let's run it again. Let's give it initial deposit of 1,000, so type in 1,000. Yeah, 1,000. Hit enter. And it says, what is the There's one right here. Go ahead and try it.